Hey Royals, welcome back. This is a solution or walkthrough on question 2 that deals with the football. Okay, so if we had a football that we were kicking at an angle of 31 degrees above the horizontal. So if this is my situation, I'm kicking a ball that way. So the angle here is 31 degrees. And I'm giving it a velocity, an initial velocity, so I'll call it V1, of 23 meters a second. And it's flying up into the air. And what I want to do is I want to find the components of the x and the y initial velocities. And then I want to find what's the maximum height that this football reaches. When does it reach that height? And then what is the actual height? So if we look at A part's asking us to determine the components. So the initial velocity can be made up of a velocity in the x direction and a velocity in the y direction. So those are the two pieces that I want to try to find for our A part of the question. So A part, if I was going to try cosine of theta tells me it's the adjacent, and that means it's v1x magnitude, because remember, trig functions don't work with vectors. They deal with scalar quantities because it's a ratio of lengths divided by the magnitude of v1. I'm going to substitute in the values I know. Cosine of 31 degrees is then going to be equal to v1x magnitude divided by 23. And so I can say meters per second. So if we multiply both sides by 23 meters a second, I get 23 meters a second multiplied by cosine of 31 degrees. That gives me v1x magnitude. So working that through, I get an answer of 19.71 meters a second, and that is my speed in the x direction. We can go ahead and write that as v1x is 19.71 meters a second, and based off of our picture here, it's towards the right. That would be the x component of the initial velocity. Same thing could happen if I was looking for the y component of the initial velocity. So I can say sine of the theta, opposite would be the v1y, divided by my magnitude v1. And let's go ahead substituting the values. I get sine of 31 degrees is equal to v1y divided by the 23 meters a second. I'll multiply both sides by 23. So I get 23 meters a second multiplied by sine of 31 degrees, and that gives me v1y. I can actually go ahead and calculate that. It gives me 11.85 meters a second as my speed in the y direction. Now we can look at our picture and say that that y direction is upwards. So v1y, the initial velocity in the y direction, can be written as 11.85 meters a second. Based off our picture here, we'll say that that is up. So there is our answer to A part. We now have the components of the initial velocity in the x direction and the y direction. Okay, so the second portion here says, when does it hit its maximum? So that's asking us for time. So I'm looking for the time that it takes to get to its maximum height. So remember, maximum height, if I take my Scottish man here, maximum height is when he reaches a maximum. So he's slowing down as he rises into the air. He's momentarily going to stop, and then he's going to start falling back towards the earth. So if that's the case, his v2y, his momentary speed or velocity at the very top of the arc, is going to be 0. Okay? So visually, what does that mean? If I were to kick a football, it's going to follow this arc. Sorry, I don't have an arrow on that one end. There we go. We're looking at this point right here, v2y, and we'll say that that's 0 meters a second. Okay, so I know its initial velocity in the y direction too. I know initially it was moving upwards at 11.85 meters per second. So I'm going to use this information along with the fact that acceleration is 9.8 meters per second squared downwards to find out how long this football is in the air. So I'm going to use here my v2y is equal to v1y plus ay delta t. Because I don't know its displacement, I don't know anything about how far up and down it goes, so I'm going to avoid any equations that use that. So this equation that we've written down right now allows us to find how long it's in the air, delta t. My final velocity, we said, was 0 meters a second. My initial velocity, 11.85 meters per second, and that's upwards. My acceleration is 9.8 meters per second squared downwards, and that's being multiplied by delta t. So I need to rearrange my equation to isolate for delta t. And that I'm going to just simply subtract 11.85 meters per second squared, or sorry, meters per second upwards from both sides of my equation. And that leaves me with this expression right now. So down multiplied by delta t. And I'm going to divide both sides by 9.8 meters per second squared down. So I'm going to divide this by 9.8 meters per second squared down. And I'm going to divide this by 9.8 meters per second squared down. And you'll notice that I have an issue here, that my numerator value is directionally upwards and my denominator is directionally downwards, but the negative sign will actually work itself out. So I have 11.85 meters per second downwards because it's a negative magnitude of up divided by 9.8 meters per second squared, giving me delta t. So if I divide that through, I get a time of 1.2 seconds. So I now know that my time that this football is in the air is 1.2 seconds. So I can say, therefore, the maximum time. The ball reaches its max height at 1.2 seconds. Okay, so now we have an expression for time that it takes to get to the maximum height. So it would be double that time, 2.4 seconds, for it to arrive back down to the surface of Earth. But we're not asked to find that. C part is asking us to find out how high does it go at its maximum height. So I can say, okay, fine. The maximum velocity, the velocity at the maximum height is 0. The initial velocity for this object was 11.85 meters per second, and it was upwards. The time it took to get to its maximum height was 1.2 seconds. And the acceleration in the y direction is 9.8 meters per second squared downwards. I'm going to use everything in the vertical because I'm asked about how high does it reach. What is its maximum height? So I'm going to go ahead and I'm going to use, I have two different ways I could do this. I can say that I'm looking for displacement in the y direction, and that's made up of the initial y direction times the time plus 1/2 of ay delta t squared. And I can substitute in all those values. I know everything except for my displacement. Or another way I can do it is I can say that v2y squared, so the vector of v2y squared is equal to v1y squared plus 2ay delta dy. And since we've been using the top equation often, I just want to go through, I'll do the second equation just so that we're comfortable with multiple different versions of these equations. But both of these would work. So the second one, it would give me 0 meters a second I square it, is equal to the initial velocity, 11.85 meters per second. And remember, when I square a vector, it becomes a scalar. So I get 11.85 meters per second, all quantities squared, plus 2 times 9.8 meters per second squared, and that's downwards, multiplied by delta dy vector. Okay, so I get 11.85. So 0 is equal to 140.42 meters squared divided by seconds squared is equal to, plus 19.6 meters per second squared downwards in a bracket multiplied by delta dy. And we can rearrange this. We get negative 140.42 meters squared divided by seconds squared is equal to 19.6 meters per second squared downwards multiplied by delta dy. I'm going to divide both sides by that 19.6 meters per second squared. So 19.6 meters per second squared downwards, 19.6 meters per second squared downwards. And if I do that and work through the fact that downwards and a negative, I would get a negative 14.32 meters down as my delta d. But we know that negative down is up, so we got 14.32 meters upwards as my displacement in the y direction. So this football hits a height of 14.32 meters. The max height is 14.3 meters for this football, for the football. Okay, so that's the solution to question or example number 2. If you require some additional assistance on this, please don't hesitate to reach out to me. Hey Royals, we're going to work through example number 3 on this lesson, and this example deals with a hot air balloon and a child throwing a ball out of the hot air balloon below the horizontal. So the angle that they throw it down at is 15 degrees below this horizontal, and they throw it at 8 meters a second. So I've drawn a simple little picture here to demonstrate what the heck is going on there. Okay, so the first part of the question, A part, is asking us to find the initial velocity in the vertical direction. So the initial velocity will be the y component, I'll call this v1y, is the y component of that vector or that triangle. Then B part asks us to find the horizontal component. So I'll call it that v1x will be B part. So that will be what we'll do for the first two. And then we're asked a series of questions about what will be the vertical distance at 2 seconds, or what will be the horizontal distance at 2 seconds, and then what is the the final velocity of this ball at 2 seconds. So let's dive into the problem. So the triangle I've set up here, if I were to use the sine of 15 degrees, I would get that it would be the magnitude of v1y divided by the magnitude of v1, which allows me to say, okay, sine 15 degrees is going to be the magnitude of v1y divided by 8.0 meters per second. If I multiply both sides by 8.0 meters per second, I can find out what the y component of my velocity is. So if I were to multiply that through, I get an answer of 2.07 meters per second as the speed in the y direction. So I can actually make that, and I can say that as a vector. I can say v1y is going to be 2.07 meters per second and we'll say it's downwards. Okay, so that is the example for part A. Part B is very, very similar. It's asking us for the x component. So part B of this is asking us to find the x. So I can say cosine of my angle, so cosine of 15 degrees, is going to be the magnitude of v1x divided by the magnitude of v1. And we'll substitute in the magnitudes there that we know. So v1x we don't know, hence we're solving for it. This is 8.0 meters per second. We're going to multiply both sides by 0.8, or not 0.8, by 8.0 meters per second. Cosine of 15 degrees, and we get v1x. And that should give us 7.72 meters a second as the magnitude of v1x. Which means that I can actually write it out and I can say v1x as a vector is 7.72 meters a second, and we're going to call it forward for this, or based off the drawing that we have. That's the direction. All right, so C part. C part asked us how far vertically does this thing travel in the first 2 seconds. So C part, we want to find out delta dy, okay, if the time is 2.0 seconds. Well, it's going to experience acceleration. So I can say AY is going to be 9.8 meters per second squared, and that will be, I'll use an arrow for downwards, and its initial velocity in the y direction is 2.07 meters per second, and that is in fact downwards. So we're trying to find out how far has it traveled. Well, I'm going to use my displacement equation. So displacement in the y direction is equal to v1y times the time plus the 1/2 ay delta t squared. So there's the equation I'm going to use. Let's substitute in the values that we have. Delta dy. My velocity in the y direction is 2.07 meters per second downwards. My time is 2 seconds. I have 1/2, I get 9.8 meters per second squared downwards. And I multiply that by 2.0 seconds, and it's squared as well. The first term here, if I work it through, gives me 4.14 meters, and that's downwards. The second term gives me 19.6 meters, not meters per second, meters, and that's downwards. And if I add those together, I get 23.74 meters, and that's downwards. So I know that this object that the child threw out of the hot air balloon is going to have traveled 23.74 meters downwards in that first 2 seconds. So D part asks us horizontally, how far has it gone? And I'll just go to the next page here. So horizontally, how far has it gone? Well, we're looking for this. So let's ask, what do we know horizontally? Well, I know the initial velocity horizontally was 7.72 meters a second, and that we said was horizontal. I know that the acceleration in the x direction is 0 meters a second, and I know the time we're asked for is around 2 seconds. So let's go ahead and use, again, the same type of equation we did for the vertical, but for horizontal. So delta dx is going to be v1x times delta t plus 1/2 ax delta t squared. Now this term here goes to 0 because I have 0 meters a second. So realistically, it just falls down to the displacement is equal to velocity times time, something that we are familiar with. So displacement in the x direction is 7.72 meters a second horizontally, multiplied by 2.0 seconds, and working that through, you get 15.44 meters a second, or sorry, meters, because I multiplied by seconds, horizontally. So my displacement in the x direction is this expression right there. Cool. So E part, in E part, we want to find out how fast is this object that the child threw moving after 2 seconds. So delta t is still going to be 2 seconds. My initial velocity in the x direction is going to be 7.72 meters a second, and that's horizontal. My acceleration in the x direction is going to be 0 meters a second squared, which means my final velocity in the x direction is going to be the same as my initial. So I'm just going to call it Vx, because the velocity in the x direction will not change because there is no acceleration in the x direction. That can't be said about my velocity in the y direction. My velocity in the y direction was originally 2.07 meters per second, and it was down. It's going to have accelerated in the y direction because of acceleration due to gravity. So the gravity is going to be 9.8 meters per second squared downwards. So first I need to determine, if I'm going to determine the overall velocity in the final situation of this case, I need to know how fast vertically is it moving at 2 seconds. Okay, so we're going to try to find this piece first. So V2y. V2y is made up of V1y plus AY delta t. We let it run for 2 seconds. So V2y will be equal to 2.07 meters a second downwards plus 9.8 meters per second downwards multiplied by 2 seconds. And if you work that through, you get an answer of 21.67 meters per second downwards. Okay, so drawing what we have here, if I draw this out, my horizontal velocity doesn't change because there's no acceleration horizontally. And if I draw my vertical, it has sped up. So my vertical velocity at the end is 21.67 meters a second downwards. My initial horizontal, which is the same as my final horizontal, which I'm just calling Vx, and I'll put little arrows above all of these because they are vectors, is going to stay at 7.72 meters a second, and we're going to say that that remains horizontal. So I want to determine this. I want V2. Okay, so when I do that, it's a right triangle. So I can use Pythagorean theorem. I can say V2 magnitude squared is equal to V2x magnitude squared plus V2y magnitude squared, which means that V2 magnitude is equal to the square root of these two values. So it's square root of 7.72 meters a second, because that's my horizontal speed, plus the 21.67 meters a second. That's my vertical speed, and I'll extend that out. Taking the square root of that, you should find you get a value of 23 meters a second. So that gives me the speed. I need the direction. So the direction is right there. Direction is below the horizontal. So I can say tangent of that angle is going to be V2y divided by V2x magnitude. Substituting our values, we get tangent theta is going to be 21.67 meters a second divided by 7.72 meters a second. And if you work that through, you get an angle of 70 degrees. So how do I summarize all this up? Well, I'm going to say then V2 is equal to 23 meters a second. The direction will be horizontal, 70 degrees towards the downwards direction. So I've now worked through this problem as well. And again, if you have any questions and concerns about this problem, please don't hesitate to reach out to me.